Welcome. We're going to spend a little bit of time now tying together a few concepts. So introducing some motion concepts, looking at some formulas, some graphs, how you might get some formulas from graphs, and then we'll do a couple simple examples as well. So what you see in front of you here is just your basic position versus time graph. The book that we're using likes to use displacement to label these graphs. I actually prefer to use position instead. The units, of course, are the same, meters, but displacement is the change in position from one place to another. And if we're looking at this right here, which we'll look at in just a little bit, this delta x, this is really change in position over change in time. So if you label this as displacement, that kind of can throw things off a little bit. But if you remember from middle school, and we all love to remember middle school, right? The dances, you asked that person to dance and they turned you down, and you cried the night away. Oh, wait, sorry, I'm getting too autobiographical. But you get the idea. So from middle school math, and some of you may have learned this in elementary school. It's typically taught in the middle school, but you might remember slope, just this general rule, equals rise over run. So rise basically means the change in the horizontal parameter. I'm sorry, in vertical, change in the vertical, vertical, no E at the end, variable divided by the change in the horizontal variable. That's probably somewhat sloppy speaking there. It's not really the horizontal variable, it's the variable that's represented on the horizontal axis. So in this case, change in is represented by the Greek letter delta. So this change in, it's just that's one way to represent that. And in this case, the vertical axis variable is position. And then change in the horizontal variable. So again, use that triangle. The horizontal variable in this case is time or clock reading. So this is the slope of a position versus time graph. And right here, slope is a generic term. So slope equals rise over run. That's pretty much as general as we can be. Scientists, when we learn things now, we oftentimes learn the terminology and then we study what that concept is. But of course, scientists and anything, the first people to discover something, they don't discover the term. Somebody didn't lift up a rock, flip it over, and say, oh, look, there's velocity. They noticed a trend, and instead of saying, this trend that relates to the ratio of the change in position divided by the change in time, that's a lot of words. They just gave that a name, and the name that they gave that is velocity. Displacement, remember, is a vector. So it has a magnitude and a direction. So that's a vector is a magnitude, and magnitude is really just another name for size. So remember, magnitude matters. So it's got a magnitude and a direction. And time is a scalar. Time does not have a direction in the sense of north, south, east, and west. You can say, well, time can move forward, or if we're talking science fiction, time can move backwards, or if we're talking about some college classes, time stands still. But for the most case, we think of time as a scalar, moves forward in one direction. Time marches on. Actually, let's leave this color the same. So this is velocity. And since change in position is a vector, then velocity is also a vector. This is really, I labeled it as velocity, but this is really the average velocity over that displacement. So I'm going to put a bar on the top here, where that bar stands for average. So indicates average. Sorry, that was not a very good-looking word there. So to complete the story, V bar means the average velocity over the interval represented by delta t. And another way to write V with the bar on the top, sometimes it's just written V av, so V sub average. So this doesn't tell us what is happening between here. So if we know, let's just say, for example, and by the way, so you say, well, why didn't he just read what was on the top? Of course, he did read what was on the top. So let's go back to just a little example, use a different color. So if we have x final equals 10 centimeters, x initial or x naught equals 5 centimeters, and delta t equals 2 seconds. And I just wrote out the word seconds because my S looks a lot like a 5, so you might think, what, 25 what? So in this case, and this is obviously a super easy math problem, it's going to be 10 minus 5 centimeters over 2 seconds, and this time I will just use that. That, of course, is 2.5 centimeters per second. All we can say is that this is the average velocity, and the magnitude, it's actually the magnitude of the average velocity because we didn't say whether it was north, south, east, or west. But this is the magnitude of the average velocity in this interval. So this is for this and I'll go 2.0 second interval. This does not tell us what the velocity is at 5 centimeters. It does not tell us what the velocity is at 10 centimeters. It doesn't tell us what the velocity is at 7.5 centimeters. All it tells us is the average velocity over that interval. So the smaller the interval, the closer this average velocity is to a velocity at any given time. Sorry, I hit the erase icon here. So our goal, and the book addresses this, we'll probably address this in future recordings, but this really is the average velocity, and all we can do is find in the practical real-world data gathering world, we can only find the average velocity over an interval. Now, we can make that interval really, really small, and in fact, even the speedometer on your car, it's giving you a reading, so 65 miles per hour. But that reading is still an average because there is a little sensor on the wheel that goes around when the wheel goes around. So all it's really doing is saying, okay, the sensor goes from top around to top again. The car knows that distance and it can figure out the time. So with that change in, or that distance traveled divided by time taken, it can then figure out what the speed is. But there is probably a slight change in that, even in that one circumference of the little sensor. Your car can't tell you that information. Your car just gets the reading every time, okay, 1 revolution, figure it out. 2 revolutions, figure it out. 3 revolutions, figure it out. So here is what we just talked about. Let's go back. Let's go to red, because I'm going to be just pretty much drawing circles on here. So here's a much neater looking version of what we discovered. So average, and by the way, this bar over a variable, that is a universal signal for average. So if we have a bar over the A, that's the average acceleration. If we had an F with a bar over it, that would be the average force. Oops, lost my little pointer here. So delta X is the change in position. And then it says or displacement. Displacement, so the or doesn't stand for change in position or displacement. It means delta X is the change in position or it's the displacement. The book likes to save ink, whether it's virtual or you're reading it online. So if we do take the initial time to be 0, then of course we can drop that. So this is saying T0 equals 0, and it's saying T final. They're just defining that. So the triple equal sign here is defined as T. So even when you see this, and you'll see this in the book, when you see this, you should think this. In my mind, I like to visualize this entire formula here. And when you're just learning physics, you're thinking, I would rather visualize the fewest amount of variables possible. And I can understand that. I can empathize with that. But it really is going to help you to always visualize the equation that's in the circle, because that really is the definition. Average velocity is not position over time. Average velocity is change in position over change in time. So if you ever see a formula that looks, in fact, this time I'll purposely delete this. If you ever see a formula that looks like this, you should say bad formula. Or maybe not a bad formula, but a formula that made a bad decision, because this is not accurate. Let's just work on a quick practice problem. So this is number 26 here, a professional application. So blood is accelerated from rest to 30 centimeters per second in a distance of 1.8 centimeters by the left ventricle of the heart. So that chamber of the heart squeezes, and just like you can take a syringe, sometimes you might squirt a syringe of something in your mouth to rinse it out, or a doctor might squirt a syringe of something, some sort of fluid in your ear. So the ventricle acts like a syringe and pushes the blood. So make a sketch of the situation. Let's see if we're on this the green color again. I don't want to use the green color. So it goes, so it's pushed a distance of 1.8 centimeters by the left ventricle of the heart. So it doesn't say what direction the left ventricle pushes it, but just so it's easier to visualize, we're going to say that it is pushed from this initial position to this final position, because then it's going in the traditional positive direction of the traditional number line. We could have these two dots any old configuration, but this is kind of rule number one. When you're making a sketch, make the simplest sketch. So this is really the simplest orientation in sketch. All right, so now what are these? It says it goes a distance of 1.8 centimeters. So all this is saying, we know that delta x equals 1.80 centimeters. This doesn't tell us specifically what x initial and x final are, x naught and x final. So we could make those two whatever we want as long as the difference is 1.8. It's like if your change in wealth for the month was $200. That doesn't tell you what you started with and what you ended with. It just tells you what the change was. So maybe for you and for Bill Gates, the change in your wealth for the month was $200. You maybe went from 400 to 200. Bill Gates went from 68,400,000 to 68,200,000. Same delta wealth. So if we're worried about the delta and not the actual values, we can make these obey the rule here of 1.8 is the delta. But the simplest thing would be to say, okay, here's where our number line starts. which means that this is where our number line ends in this case. It's eventually going to ask us how long does the acceleration take. So we're going to have a t0, so a t initial, and a t final. So how long means, oops, delta t. So again, we can set this up however we want because delta t is the important thing. So we can do what we did on the previous slide, what the books likes to do, and is set t initial equal to 0, which means we don't know what t final is. It's accelerated from rest to 30 centimeters per second. So v0 equals 0, that's rest. V final equals 30 centimeters per second. It says it's accelerated. We don't know what that acceleration is. Maybe we'll need to know, maybe we won't. All right, so we've made the sketch. List the knowns. We've listed the knowns. How long does the acceleration take? To solve this part, first identify the unknown and then discuss how you choose the appropriate equation to solve for it. I'm sorry, how you chose. I'll learn how to read one of these days. How you chose the appropriate equation to solve for it. After choosing the equation, show your steps for solving for the unknown. So if we want to know how long, so we know delta x, we know v0, we know v final, and we know, sorry, we don't know. Don't know anything else. Our unknowns are acceleration and t final. So we are looking for an equation here that has that has these velocities, it has a delta x, and it has a t final in it. That would be ideal. We could look for an equation that has acceleration in it, but we don't know acceleration. So that would give us an extra step that we probably don't need. It'd be a headache that we don't need. So we know definitely, so one formula is the only one we've determined so far. Average velocity equals delta x over delta t. And if we plug in from above, that's x final minus x initial over t final minus t initial. Well, we said that this was 0. This was 0. So that simplifies to x final minus t final. So I said before, earlier here, if you come across a formula that looks like this, That's a bad formula. We didn't come across this formula, though. We made some simplifications, and it reduced to a formula that looked like that. That's okay. All right, so now we have v bar, our average velocity. I'm going to make this a little bit better. So how does v bar relate to v final and v initial? So if we look back to this graph here that we had on the very first one, so we've got v, we have, oops, sorry, wrong graph. We don't want to do that. Forget that I said that. Block that out of your mind. I was thinking of something else. So it doesn't say here whether or not, it doesn't say anything about the acceleration. So we need to make an assumption here with the acceleration. So if the acceleration is constant, then the average velocity I forgot to spell average there for a second. Average velocity is just the mathematical average of the initial and the final. So the mathematical average would just be v final plus v initial over 2. So we have two equations. We've got equation 1, equation 2, and we don't know what v average is, but we do know all the rest of this, and we also know that this is 0. So I'm running out of space. So you're thinking, man, that's pretty tough. How's he going to do it? Well, I planned ahead, baby. So we've got, oops, I almost didn't plan ahead, though, and used the color that's a little bit more difficult to see. So we have this equals v final over 2, and we also know that it equals x final over t final, so we can combine and then we can cross multiply. So we get t final equals 2 x final over v final. And before we go on, let's do a quick unit check. Check the dimensions here. So position here is in meters. velocity is in meters per second, and usually dimension, when you're checking dimensions, put brackets around like that. So meters cancel with meters. This is in the denominator of the denominator. So that is units of seconds, which matches what it should be. Two times x final, which was, and we were given, oops, here. So 30 centimeters per second and 1.8 centimeters. .8 centimeters divided by 30 centimeters per second. And I apologize, so when I did my unit check here, I did meters divided by meters. As long as it's the same unit, of course, they're going to cancel each other out. And that comes out to be 0.12 seconds. So is that reasonable? About 1/10 of a second. So if you think of your heartbeat, I mean, it's difficult to time your heartbeat, right? But if you take your pulse here, I know I'm holding my arm up high, but that beat happens pretty quickly. So if I just count 1/1000, the beat just seems to take a very short part of that. So it kind of makes sense that it takes well under a second. But not an unbelievably tiny amount of time. All right. So accelerated motion. Notice the difference here between uniform motion. So notice that, and again, it uses displacement. I prefer position. Because each one of these numbers represents a position. So it's okay to say this represents jet car displacement, because we typically, especially if we're looking at trends like we're looking at here. So notice the position versus time graph is curved. And for uniform motion or constant velocity, it was straight. Notice that the slope, so this is a small slope, which means small velocity. This is a big slope, which means big velocity. So the small slope so where there is a small slope, that represents a small number. On the velocity versus time graph. And this represents a large number on the velocity versus time graph. So the slope of the position versus time graph is a velocity versus time graph, and that matches what we learned before. Here was the position versus time graph, and the slope was velocity. Here's the position versus time graph, and the slope is velocity. In this case, that velocity is changing. So if we look at the slope of this graph, if you remember back from middle school, so middle school, there's the disco ball in the ceiling. Usher was singing Yeah, probably not in your middle school, but a recording of him was singing that. So the slope here is rise over run. In this case, the rise is change in velocity. The run is, again, change in time. And again, scientists look for a pattern, and then they give that pattern a name. So this pattern of the ratio of the change in the velocity to the change in the time, they gave the name acceleration. So the slope of the velocity versus time graph is acceleration. And because this green graph here has a constant slope, it's an upward trend that goes from a small number to a big number, but it goes from that small number to that big number uniformly. So that's going to be a flat line right there. So to kind of break down what we did before, just to review, slope, this is the most general. And then when we have the rise is V final minus V initial, the run, T final minus T initial. And that's defined as acceleration. And just like before, this doesn't tell us the acceleration at any specific time. All this tells us is the average over the calculated interval. And by the way, let's just take a quick look at that again. So this means is defined as so you can't derive this equation. You know how some equations you can derive, you can combine some equations together and get a third equation. This isn't derived, this is a definition. This is saying there's a pattern in nature that's useful. That pattern that's useful is the ratio of the change in the velocity to the change in the time. Because it's useful, we're going to give it a name, right? So taking some bread, flattening it out, putting tomato sauce on it, putting cheese on top of it, putting vegetables on top of it, that's a useful relationship. So we give that useful relationship a name, and that name is pizza. So you can't derive pizza. Pizza is that thing which is the combination of bread, cheese, sauce, and stuff. And you could argue maybe you don't need the stuff, maybe just bread, sauce, and cheese. You can't just say just bread and cheese because that's a grilled cheese sandwich. Oh, that's a good question. Is a grilled cheese sandwich a subset of pizza? That's a philosophical question for another day. Let's just go over a quick problem to apply this formula here. So we've got an intercontinental ballistic missile. So if you've ever heard the term before, ICBM. So ICBM, that doesn't mean I see a ball movement, it means intercontinental ballistic missile. So it goes from rest to a suborbital speed of 6.5 kilometers per second in 60 seconds. Oh, look at this, trying to be all fancy. Ooh, the actual speed and time are classified. So if we draw a picture of this then, so down here, and it goes up to here to some certain speed. So it starts down here, and we're not given any information, so we'll just measure our ruler from ground level. X final, don't know that. It says it starts from rest, so V0 equals 0. V final equals that was pretty ugly looking 5 there. .5 kilometers per second. That kind of looks like Herman Munster's forehead there. And in a certain amount of time, so from some initial time, all we really care about is delta t, so we'll start our clock when it takes off. T final equals 60 seconds. And we don't know what the average acceleration is. And we want that in meters per second squared and in multiples of g. So we know that, first let's convert 6.5 kilometers per second to meters. So 6.5 kilometers per second. Remember, unit conversion is just a fancy way of multiplying by 1. So we know that 1 kilometer equals 1,000 meters. So it's going to be 6,500 meters per second. So now we want to know the average acceleration. Well, average acceleration is change in velocity over change in time. So we don't know the final position, but we don't need to know that. So sometimes you'll have an unknown and you just don't need to know. It's not part of the equation and it's not being asked for. So V final minus V initial. Let me just quickly cancel these units here. So that's how we end up with meters per second over T final minus T initial. So that's going to be 6,500 meters per second minus 0 divided by 60.0 seconds minus 0. So that comes out to be, let's see, what number did we get here? 108 meters per second. So we've got a meters per second on the top divided by a second. Some people like to write down meters per second squared. I prefer the term myself, meters per second, because that really sort of hides the definition within it, or I shouldn't say it hides it, it reveals the definition, meters per second, velocity per unit time, Meters per second squared almost looks like it's a distance or a position or a displacement divided by time squared. So in multiples of g, so to find it in multiples of g, we're going to divide our value, it's kind of a sloppy looking bar, by g. And we don't care about the sign of g. Typically, g is described as negative 9.8. Here it's stated as positive 9.8. G is an acceleration that is directed towards the center of the Earth. A is an acceleration upward in this case, but that's not what is relevant in this case here. We just want to know the ratio of their magnitudes. So 108 meters per second divided by 9.80 meters per second. Units cancel out, which is good, because a ratio like that should not have units. And it turns out that the answer is 11.1. So that means that A equals 11.1 G. And pilots black out at G-forces much less than this. So if you were riding on an ICBM, you would black out. Of course, once the ICBM hits something and blows up, you're probably in a worse situation than just blacking out, but that is what indeed happens. All right, so hopefully you're feeling a little bit better about this sort of thing. So key issues here: slope of a position versus time graph is velocity. And if the velocity is constant, the position versus time graph is a straight line. And in fact, that's how we derive the average velocity equation, is from that graph. And then we went over an example here, practice our problem solving. Similar for position versus time for accelerated motion. Here, it's an upward curve. The object is speeding up. So the slope is not the same throughout. Small slope, medium slope, big slope. Or I'm sorry, small slope, medium slope, big slope, which corresponds to a small number on this graph, medium-sized number on this graph, large number on this graph. The slope of the velocity versus time is acceleration, and since the slope is constant throughout this green line, we're going to get, average size slope, average size slope, average size slope, because we've got average slope, average slope, average slope throughout. And that's how we can derive average acceleration. So hopefully you learned something, and I think it really helps for understanding to relate the formulas back to the graphs, because some people like to look at formulas, some people like to look at numbers, some people like to look at graphs. And if you can really tie all those three together in your mind, you'll get a better understanding. Thanks, and we'll see you later.